All right, so we've developed our criteria for system stability, but now we want to figure out, okay, well, how can we create a controller, right? Because again, this is a controls class. There's going to be some type of controller, and we need to figure out, well, how can we ensure that we can adjust the controller values to make sure that we are indeed how can we address the controller? How can we address the controller values to put us in a stable system, right? Or to make the system stable. So that's essentially the goal what we're doing here, and we're going to kind of go back to our transfer function for the whole Unity closed loop system. So remember our old friend Unity feedback with a controller. So if we're looking to develop the transfer function for this Unity feedback system with a controller, we know how to write it out. So C, it's the output controller command over the input, which is the air. Air is defined as R minus Y. You see here, the plant is output input here. And now we can do some algebra and rearrange that system. If you remember back all the way to lecture 7, we actually found this closed loop transfer function, which is output over the input or the reference of our system, which is the input. And this is our closed loop transfer function. And you see the poles of the system are going to be governed by this. And the controller and the plant are what really determine the stability of that system. So we're going to choose what is our C, our controller in the Laplace domain. One of the simplest ways to start with a controller is just using or setting a value, right? So I'm going to say my controller, and it's set to a constant, and this is like a gain, or actually control. We'll get to that in a bit. I don't want to give away the game, not the gain, but anyways, or basically a proportional feedback. Anyways, it doesn't matter. Let's just set our C of S to some constant. So our closed loop transfer function, we're just substituting in here, and let's say we have a P, or our plant function is this. Now our closed loop transfer function becomes this, and then now the poles of our system, the stability is solely determined by this. So when we set this equal to 0, our poles, if k is less than a, the pole will be in the right half plane and we're unstable. If it's equal to a, we're marginally stable, and if k is greater than a, we're going to be in the left hand plane and we're stable. So here you can take a system. And if a is greater than 0, we know, basically S equals a, that's a right-hand plane. This is an unstable system. But by tuning our parameter k, by tuning our controller, we can make a system that's inherently unstable stable. And that's really, really cool. And it's the first example of, again, how do we actually control a system? How do we prevent a system from becoming unstable? How do we push it into a stable regime? This is nice, but this is a first-order plant function. How do we go through something a little bit more complicated? What about if you were given this plant function, or actually, this is the poles of your system. Let's look at this transfer function. And I'm going to pull up Mathematica here. How can we determine if this system is stable? Can we just look at the coefficients? If we just look at the coefficients and they're all greater than 0, it should be stable, right? Unfortunately, no, it's a third-order system, so we have to do Routh-Hurwitz. So we're going to say 1, 5, coefficient, k minus 6 is our coefficient, and then k. So our Routh-Hurwitz table becomes this, and now we have some conditions, right? We know that our values here in this first column must be positive. So we can say, well, I need to make sure, for example, here, this one's pretty easy in the bottom here. So k has to be greater than 0. So that's already one bound. So we have one bound where k has to be greater than 0. We also see that in here, k has to be greater than 7.5, right, to keep this positive. And we can just double check that. I always get stuck on the greater than that. I can make mistakes occasionally. Yeah, so you can just say less than negative. So see, it has to be greater than 7.5. So, and k has to be greater than 7.5. So if these two conditions are met, we're going to be stable. And we can kind of see that here. But the cool thing is we can actually visualize it as well. So I love, I'm mean, I love Mathematica, period, but I really love the fact that we can like visualize a lot of these, the systems and the behavior as well, right? So I'm going to go ahead, I'm going to set up, this is our g of s. So for this transfer function, I can see if my k is 5, right, I have two poles that are in the right-hand plane. That's an unstable system. Agreed? And you can see that right there. And we can see the real part is positive. If I switch it to k is now 10, now I'm pushing it and I'm in the left-hand region for everywhere. So negative, 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 everywhere. And I have how many poles? I have 3 poles. And you can see poles and then the 0 as well, which is very cool and interesting. We can actually, and one of the cool things we can do with this, that's our, let's say if we had an input, I'm trying to visualize and show. Let's say our R of S was just 1, right? So for example, we see the poles and we know it should be unstable. But let's say our G of S is equal to Y of S over R of S. Now I'm going to say our R of S is just unity. And so what we can do is we can say, well, okay, now I want transfer, and we can actually see that here. Let's do transfer function model of this. And now I want inverse Laplace transform comma S comma T. So I want the inverse Laplace transform of this function. What don't you like? Why doesn't it? I could maybe just put it like this. I think sometimes it doesn't like the. Let me see. Or maybe I can just do. I think I have to do this inverse. This is just and apologies for this. GS/.k goes to 10. And then ST. All right, so I'm going to call this my YT test. I'm going to do this, I'm going to hide this, and I'm going to say plot Y test T from 0 to 10, comma, plot range all. So is it a great system? No, it's pretty sinusoidal. I mean, it decays. It's pretty it's decaying. What if we do 100? And then let's keep the same. You see here, we're killing that because we're getting more stable. But what if we do 6? And then I'm going to be really in trouble here. My computer might break. You see, we're flat, but then we start to get resonance. So you see, unstable system. This is why I love Mathematica. I mean, you can see everything physically. And again, this might just be for me, but I really have to do this to really understand my system. So, fantastic. All right, let's get back to our notes here. So here we're again seeing how a controller can keep us stable. So this is fantastic. There are some implications for controller design. So that K is what's called, again, a simple game. It could be proportional, it could be integrative, derivative, et cetera, et cetera. But again, our control objectives, which we kind of talked about, overshoot, settling time, rise time, et cetera, it's going to depend on the root of the system. So you have to kind of change the shape and location of essentially those poles in that S domain, right? So we have to change where these occur and how the system shape will respond based on that. So that's our goal of that controller design. You can also destabilize a system. There are certain examples where if you poorly choose, you can push it too far where you're going to change, again, essentially the poles or the shape essentially of that system. So it's really, really important that you have to verify essentially your stability through essentially these different tests or criteria or conditions. And it's really, really important that you do so. It's also important, again, you have to kind of think about the whole design of your system, right? Where can there be disturbances? Where can there be essentially noise in the sensors? We kind of talked about this a little bit in lecture 7 as well. And again, our objectives always have to be, we need to be stable, track, which means Y should follow reference, disturbance rejection. So we should stay close to R of t even if we do have some disturbances. And we need to minimize essentially of t to prevent essentially damage. Like this is our control command. When we increased, for example, that k gain, you can think of it. It could be like the signal that's sent, that control command. It could be horsepower. It could be torque. It could be lots of different kind of inputs. And you could just be plugging in a value that's not even feasible or so expensive where it's not possible to control that system. So we have to kind of think about that and the trade-offs and trying to make sure that what we're developing is actually a realistic system. So let's go ahead and let's finish up before we get into some block diagram review, just the kind of the trade-off. So remember, if we have this plant we have here, we have our transfer function, it shifts here. So there's benefits of larger K. So we're going to reduce the error, we're going to get faster response, so shorter settling, basically a settling time, improved tracking. So Y of t is closer to, matches closer to R of t. But again, you can, blow out that motor or whatever. There's limitations on essentially your actuator system. And again, you can destabilize it as well. So next time we're going to get into block algebra, looking at these transfer functions for different control architectures, and we'll see you next time. Thanks. Bye.